All right, let's take a look at our lesson for today. So today we're going to be looking at a little bit of a different take on volume. This volume has to do with rotations. It's a revolution or a rotation. And so before I start on the problem, what I would like to do is kind of show you I guess it's like a visual of what we're going to be doing. Okay, so let me pull up this visual. So this is an example. Let's just kind of get this in perspective. So this function is square root of x. And what we're going to be doing, our first day in this is disks, and I'll talk about that in a moment. But our axis of revolution is the x-axis right here. So what this procedure we're doing, this blue part right here, that's the blue part that is underneath the square root of x and between a and b. Okay, between a and b. And what's going to happen is that we are going to visualize that this blue section right here is going to be rotated around the axis of revolution, this axis of revolution right here. And so this is a picture, and I'll just of the figure that we're actually going to be calculating the volume of. And so it's sometimes kind of hard for students to understand what we're really calculating. But as you look at that, I want you to think about the cross section. You see the cross sections are there's three of them that are kind of highlighted right there. What shape do you think those cross sections are? They're circles, right? They're circles. So in reality, this is very much like doing the cross sections, doing our volume by cross sections, because the formula is actually pi r squared. We're integrating pi r squared. We're just integrating a circle. So that's what you visually would see. That's what you would be would be finding the volume of. So let's look at our example. And so our formulas that we would be using have to do with, or they're contingent upon, what kind of axis we're rotating about. If we're rotating about a horizontal axis, then we're going to use this formula. It's going to be pi integral a to b of radius, and I'm just going to say r of x, a formula for radius squared. It's just pi r squared. That's what the formula we're going to be needing. On the other hand, if we're going to be rotating about a vertical axis, it's a vertical axis of rotation, we're going to use a different formula. This would be also pi, c to d, and I'm just changing the letters so we know that those would be y bounds of r of y squared dy. So the only difference in the formulas is dependent on the axis that we're rotating around. And the difference is if the axis is horizontal, we need to use x's. And if the axis is vertical, we need to use y's. And that is like non-negotiable. We don't have a choice. We have to go by whatever axis we have. This is a picture, just a visual picture. In this picture, the curve would have been this part right here, right? This top curve. And they would have been rotating around this axis, the x-axis. And I usually put one of those circly things to show the axis of rotation. And as you can see visually, as we would rotate around this axis, it would create a solid figure. And that's what we're going to learn to find the volume of. This technique is called with disks. And the technique we're going to be learning the next class is washers. It's the same scenario. We're going to be rotating, but the difference, and I just need to point this out right now, the difference is the disks. The disks are the area that we are rotating is sitting on the axis of rotation. If we go back to this here, notice how this is sitting on the axis of rotation before it rotates, right? That's what it's doing. It's sitting on the axis of rotation. It's making a solid figure. What we're going to be doing next time is we're going to be moving the axis of rotation, and we're going to be rotating it, around a So notice this blue, this area right here is not sitting on the axis of rotation. What happens when we do that is it creates what? What is going to be created in the center of this volume, this figure, this three-dimensional figure? It's going to have a hole, right? That's called a washer. We're doing that next time. Okay, so the one thing I want you to be sure you understand is the reason it's a disk is because the entire side of the figure is sitting on the axis of rotation. Okay, questions about that so far? All right, so then let's take a look and let's set up our very first one. I got to break it to you. Yes, remember all the graphing you've been doing like forever? Like how long you've been graphing? Like years. And you probably wondered, why am I doing all this graphing? There's so much. Well, this is why it's calculus, because we need to know how to graph these things without a calculator. Sometimes we get to use a calculator, sometimes we don't. So we should be able to graph without a calculator. So that's what we're going to do. We're going to graph this figure. So I'm going to draw my axes right here. Let's see, we have y equals e to the x. And I know that if I do e to the 0 is 1. So I know that it's going to cross, right here at 0, 1. I know that's what's going to happen. So I'm just going to, sketch the rest of it. Not a real big deal. You don't have to be perfect. Just sketch it. There's our e to the x. Okay, y equals 0 and x equals 0. These are just the axes, right? Y equals 0, x equals 0. These are just the axes. And x equals 3. X equals 3 would be, right here. And so it was talking about, we're binding this up. So this is the part right here that we're going to be rotating. It's the part bound by those 4 equations. Okay, so this is the part we're going to be rotating. Now, they want us to rotate about the x-axis. So I'm going to draw, I typically draw the axis of rotation with a dotted line. You don't have to do that if you don't want to. But I usually do. I usually draw it with a dotted line. And I usually put this little circle-y thing. This shows the axis that I'm rotating around. I just like a circle with an arrow. That's the notation I use. I mean, you don't have to use that notation, but that's just telling me that that's where I am rotating. Okay, so what our job is going to be is to find, our formula is, I'll just write this up here, pi integral a to b of big R of x squared dx. I mean, that's our formula. So I need to figure out what r of x would be. So r, and it doesn't matter where I draw my representative, I'm just going to do like a cross section. I'm going to go from here, to here. I can draw it anywhere inside the pink area, anywhere. I'm just picking that place randomly. This is my r. That's going to be r. And what I like to do is I like to go ahead and write out the equation, the expression for r. What is r? What is this going to be? So r is going to be, let's see, big minus little. So this was big, right? And this is little. So big was e to the x minus little is 0. So that's my r. Okay, so I'm going to pause here for just a second. Is everybody okay? Okay, so now I'm going to set up my integral. I've got that scenario. I've got it graphed. I'm feeling good about this. I know what big and minus little is. So I'm going to go over here. We're going to do the integral, pi times. I will tell you, this little guy right here is probably the most forgotten thing in these problems, is this little pi. Please make a note to yourself. Please do not forget the pi. Okay, poor little thing is like the most forgotten, poor thing. So we don't want to forget it. Our beginning x value, the beginning of this pink figure is 0, and our ending x value is 3. So I'm going to integrate from 0 to 3 of r, which is e to the x squared dx. Now, for today, this is the only one that we're going to do by hand. The rest of them, it's going to say either use a calculator or, or just write it up and don't solve it. So we're going to do this one by hand just for a little practice with our baby U sub. We've been having a few issues with this, so we're just going to go for it. So we're integrating 0 to 3 of e to the 2x dx. That's what we're doing. So I'm going to erase this right here. So what will we do? This is a U sub. It's a baby U sub, which means many of us can do this in our head, but some of us that are doing it in our head aren't quite making it come through properly. So let's do it by hand. So U would be 2x, du would be 2 dx, 1/2 du would equal dx. I'm going to change my bounds. So let's make a bound changing part. So u would be 2 times 0 or 0. That's the lower bound. And u of the upper bound would be 2 times 3 or 6. Okay, so I'm going to rewrite my integral with the u stuff, and I'm not going back. I'm not going back to the regular. Which one? U equals 2x, this one?
Yeah, what's under?
Du equals 2 dx.
No, like in the second bracket.
Oh, here. Oh, sorry, that's an L. U for the lower bound. U for the lower bound is 2 times 0 equals 0, and U for the upper bound is 2 times 3 equals 6. Okay, so the choice is, if I change the bounds, then I'm staying with U and not going back to x. If I don't change the bounds, then I have to go back to x. I have to put the x back in. I don't want to put the x back in. Okay, you have a choice. You can do either one, but our problem is some of us are mixing those choices up. Some of us are changing the bounds and going back to the x. You can't do that. It's one or the other. So these here are x bounds, and they belong to the x. These are x bounds, and they belong to the x. That's what they are. The one I'm getting ready to write, we'll do that right now. The one I'm writing is, so it's 1/2 pi integral 0 to 6 of e to the u du. E to the u du. These are u bounds, and they belong to the u. Okay, and we cannot mix them up. It's one or the other. Is everybody okay? I want to stick with changing the bounds and sticking with u. That's my choice. You don't have to do that. You can keep 0 to 3 and go back to the x. It's totally up to you. So let's do our antiderivative. So the 1/2 comes forward. The antiderivative of e to the u is, e to the u. I'm going to evaluate it from 0 to 6. Where did this 1/2 come from? Where did that come from? It came from here, right? We can't forget that part. Came from there. Okay, so now we've got pi over 2 times e to the 6 minus e to the 0, which is pi over 2 times e to the 6. What is e to the 0? It's 1, and we need to definitely know that. And then that's my volume. And this is volume equals. If you want to put volume equals, you can. And that's our very first problem with rotation. Okay? Now we're not going to do any more by hand. Okay, we're not doing any more by hand. We're just going to either just write it out or use our calculator. Okay, questions so far? One thing that I want to make sure, let's just write this little note out to the side. This is just for our benefit. Right now, it doesn't seem to matter, but it will. So let's just put a little asterisk here. We measure the radius from the axis of rotation. Right now, it's like no big thing because, you know, it's just right there, but this is going to be a problem or a consideration for us in future problems. The radius is always measured from the axis of rotation. Wherever the axis of rotation is, doesn't matter. That's where it's measured from. Okay? All right, so let's go to the next one. So we've got a region bounded by a line and the axes. Revolve this region around the y-axis. Oh, set up the integral to find the volume. Do not solve. Okay, we can do this. Let's graph first. So we've got here. The way I like to graph lines, I don't know about y'all, but the way I like to graph lines is I like to graph the y-intercept. And then I like to just do the slope. You know, that's -2, so down 2 over 1, down 2 over 1. And we're bounded by y equals 0 and x equals 0. We're bounded by the x-axis, so we don't really need to go any further than that. So the area that we're going to be rotating is this part that I'm highlighting in pink. This is what we're rotating. Okay, let's see what they want us to rotate around. They want us to rotate about the y-axis. Okay, so what I would do is I would put a dotted line on the y-axis and then put my little circly thing right there on the y-axis. That's what I would do. Okay? Since we are rotating about a vertical axis, what variables do we need to use in our formula? Y's. We have to use y's. So before I can get there, I need to figure out what my, r is. So it's going to go from here. All right, it's going to go from my axis of rotation out to the outside of the figure. This is going to be r. And since we're with respect to y, this is our big. Right? That's our big, and this is our little. Big is going this way for y's, and little is going that way. We remember that? We okay? Okay. So I need this line to be an x equal equation. It's not right now. It's a y equal equation. So I need to do a little bit of algebra to make it kind of, what I need it to be. So I've got y equals 4 minus 2x. I need it solved for x, so I would move the 2x over and move the y over. That's, of course, y'all know algebra. You can solve it a bunch of different ways. So then I would simply divide by 2. So x is going to be, 4 divided by 2 is 2. X is going to be this. Okay, so this is my big. My big is going to be x equals 2 minus 1/2 y. And my little is going to be x equals 0, which is kind of handy. It's kind of a non-issue, right? With the little is 0. It's not really a big deal. So if we set up our formula, we're going to set up our formula for r. R is going to be big minus little, so 2 minus 1/2 y minus 0. That's r. Okay, how are we doing? All right, so let's set up our little formula, and actually we're not solving it. We're just supposed to set it up and then we're done. So here we go. So we've got pi integral. Now we are going with y's, right? And from my graph, it's pretty good. It's not a great graph, but it's pretty good. I can see the little y is 0 and the biggest y is what? 1, 2, 3, 4, right? The biggest y is 4. Okay, and then my r is 2 minus 1/2 y squared dy, and they just want us to stop there. Okay, we're just stop. They say do not solve, so we won't solve. Okay, questions on number 2? Okay, let's move to number 3. We good here? Yes? Okay, let's move to number 3. Okay, so we've got 3 minus x squared and y equals 2. Revolve about the line y equals 2. Oh, we're not revolving on an axis. Okay, this is going to be a little different. That's good. So let's first draw our picture. And by the way, the graph is non-negotiable. You're going to have to graph every single problem that you do with area and volume, you have to graph. That's like a total requirement for me because you've got to look at it to see what's big and what's little. How do we even know if we don't graph it? What do we guess? Guess is not a good thing. So this line, this parabola right here, we should know how to graph this. We should know that this is shifted up 3 and is going down, right? Just by looking at this, we should remember from our previous math classes that this is shifted up 3 and it goes down, and it's a standard parabola. So over 1, down 1, over 1, down 1, over 2, down 4. You know, that's just how they work. Over 2, down 4. Okay, and so we look like this. And that's our parabola. And also, we are about the line y, so we're bounded by the parabola and y equals 2. So let's draw y equals 2. So y would be 2. That would be this part right here. All right, that's y equals 2. So the part that we're going to be rotating is this part right here. Okay, we're rotating that part. And our axis of rotation happens to be y equals 2. So I'm going to draw the axis with dotted lines because that's just what I like to do. So here's my axis. I'm going to put my little circly thing on it. And that's the axis we're rotating around. Since it's a horizontal axis, then it's with respect to x, right? So let's label our big and little. Okay, this is big right up here, right? Big is on top. So big would be, what is big? It's y equals 3 minus x squared. That's big. Little would be the underneath part. You know, that right there would be little. And little is y equals 2. That's little. So r, and I'm just picking a random spot to draw r. This is r. Okay, that's r. R is big minus little. So r is going to be big, which is 3 minus x squared, minus little, and little is 2. That's r. Now, this is a calculator question, and I will just tell you, I would not combine like terms. I know y'all are probably brave, and you're probably going to think, oh yeah, 3 minus 2 is 1, and put a 1 there, but I probably would mess it up. So I would just put it in the calculator just like that. Now, how do we figure out what the bounds are? Now, from my graph, I mean, it looks pretty good, I think. It looks pretty good that I've got here and here. They look like integers, right? -1 to 1. What if I wasn't sure? I would set them equal to each other. And so just for fun, because y'all know I love fun. Okay, I know we have different ideas of fun, but that's still, it's okay. 3 minus x squared equals 2. That's what I would do. I would set them equal to each other and make sure. So I'm going to move the x squared over, and I'm going to move the 2 over. And sure enough, x is plus or minus 1, which is what my graph shows. So I have pi integral -1 to 1 of r squared, which we've got right there. So it's 3 minus x squared minus 2 all squared dx. And I seriously would put it in my calculator just like that. And this is one where I did, and I put it in my calculator, and I know y'all are great with the calculator. I don't think you need me to put that in the calculator. We would just do that. And this should give me 3.351. And that's the third one. Okay. We doing okay? Okay. We have just a couple more. And then we're done. Hopefully we're just rocking and rolling. We're doing great. Yes, I have to admit, I do have a typo here. I know. Has that ever happened to us? With a typo? It happens to me. This is wrong. Right here, if you cross that out for me, please, and write in x equals 1 here, that would be great. I just had a little bit of a typo when I was typing this up. Okay, so if you'd fix that for me, that would be wonderful. Now this one, it looks weird, right? X equals 2 minus y squared, x equals 1. Do we remember from our pre-cal days what this looks like? Remember, it's a sideways parabola. Remember that? Back in the day, sideways parabola. So yes, you would be expected to graph a basic sideways parabola. There's nothing too crazy about this one. Y'all are thinking, yeah, it's sideways, it's crazy. But it's okay. So what does this tell us? This tells us that we would shift 2 to the right, and it would be upside down. But for this, upside down means pointing left, right? Pointing left. So this one would be, let's make it pink. So it'd go here, 2, and then it's going to open left because it's negative. So up 1 over 1, up 1 over 1, up 2, 1, 2, 3, 4. Down 2, 1, 2, 3, 4. Okay, so it looks like this. Okay, and the line x equals 1. Okay, that's way back here. So x equals 1 is right here. So the part that we're rotating is this part right here, this little piece. So how are we rotating? We're rotating about the line x equals 1. Okay, so I'm going to draw my dotted line at x equals 1. So that's how we're rotating. Do my little circly thing. And that's our graph. So big is going to be to the right. This is big over here. This is big. Big is x equals 2 minus y squared. All right, that's big. Little is the green one, right? Little is to the left, so this is little. And little is x equals 1. So R would be like this, like from here over, right? This is R. R would be, see how handy big minus little is? Have we embraced big minus little yet? I hope so. It makes our life easier. Big is 2 minus y squared minus little, and little is 1. Okay, so here we go. If I don't know, and am I going to have x bounds or y bounds? I'm going to have y bounds. If I can't figure out what these y bounds are, we know what to do, right? We set them equal to each other. But the graph is, I think, pretty clear, actually, what they are. So let's just go with the graph. And so integral, so pi, don't forget your little pi. So we're doing -1 to 1 of 2 minus y squared minus 1 squared dy. And it says we'd stick it in the calculator, which I would do, and I did, is 3.351. Okay, are we okay? One more. And as I was working these problems, I think it's very strange that the answers to number 3 and the answer to number 4 are exactly the same. Don't you think that's weird? It's so weird. They're two different figures, but they're very similar because they both involve parabolas, right? And a piece of the parabola. So whether I put my parabola sideways or upside down, that piece of the parabola, that's going to be the volume of the solid that's being rotated. Fun. Okay, last one. Here we go. So let's graph this, find the volumes, set it up. Okay, good. So it's here. Okay, so y equals 2 to the x minus 3. Okay, so we need to think about how to graph this. We should be able to graph this. Okay, and y'all are like, no way. Well, what does that mean? That means the exponent has been shifted down 3. Okay, so I want to know what's happening when x is 0. That's what I'm wanting to know. So if I put a 0 in here, I've got, see, 2 to the 0 is 1, 1 minus 3 is negative 2. So it's going to cross right here. That's what I want to know. That's all I care about. And then I know it's not supposed to go past negative 3. But again, we're just drawing this. It's just a sketch. Just a sketch. There's our sketch. Okay, I don't think it's curvy enough. Okay, why can't I leave well enough alone? I don't know. All right, there we go. So that's that. And we want to be bounded by y equals negative 2. Okay, so that's this part down here. That's y equals negative 2. And we want to be bounded by x equals 3, which is this part right here. So this is the part right here that we are rotating. This part right here. So what happens is this down 3 right here is talking about the, you know, this little guy right here, the asymptote that goes with him. The asymptote is down 3 right here. And where would this really be crossing the y-axis? It would typically be crossing right here. Right, that's where it would cross, and that is down 3. Right, because the e to the x guys, they cross at 1 when y is 1. Okay. And so that would be down 3. Is that okay? Okay. Whoops. Got a little crazy. Okay. All right, so let's see. We're rotating about the line y equals negative 2. So I'm going to draw my little dotted line business down here, which I normally do. And then put my little circly thing. That's where I'm rotating around. It's a vertical, excuse me, it's a horizontal line. So my R is going to be this way. Right, this is R. And so big is up here. This is big. Big is this, so big is what? Y equals 2 to the x minus 3, right? And little is down here, and little right here is negative 2. Y equals negative 2. That's my big, and that's my little. Okay, see how we're doing the same thing over and over and over again? I hope that that really resonates with you, and you can really just kind of take this and run. So my R is going to be big, which is 2 to the x minus 3, minus little, which is negative 2. That's my R. And they don't want us to evaluate this, so we're just going to write it out. Pi integral. So I think it's pretty clear what my x bounds are. Are y'all okay with that? That x is 0 and then x is 3? Okay, we go from 0 to 3 of R, which is 2 to the x minus 3 plus 2 squared dx. And again, I'm just going with my normal pattern of not combining like terms unless I'm doing it by hand. All right.